So welcome to the third lecture. So today we'll continue with, we just started on grammars last lecture, so we'll continue with it and go in some detail. So let me just briefly summarize what we did in the last lecture. So as I said, a grammar is a four tuple consisting of a finite set of non-terminal symbols or grammatical categories, if you like, as a finite set of terminal symbols which usually constitute the vocabulary of programming language, a finite collection of formation rules or productions which are really rules of replacement, and a start symbol which really signifies the grammatical category called a sentence of the language, of a language. Yeah, so we went through one simple grammar, for example, for the generation of Boolean expressions, right? So we have these various syntactic categories here. So we have the set of non-terminals or the grammatical categories consist of essentially AND expressions, the V stands for OR expressions, the C stand for conditional complement expressions, and there's a start symbol. The terminal set consists of open and closed parentheses and the connectives AND, NOT, and OR. Right. I will normally, while we are dealing with grammars, I will use the color black for terminal symbols, and since the grammatical categories are a level of abstraction higher, I will use green, light green for some things and dark green for some other things. Okay, so this was the grammar we had. We also saw how a sentence, which is a string of terminal symbols, can be generated from this grammar by applying the rules of the production rules, right? So, and in each of these cases I have circled in orange the non-terminal symbol which I am replacing, and of course I have several choices for replacing S, and I could choose one of them, right? So if you choose different choices, then you will get a large number of other sentences. You will generate a large number of other sentences. In fact, since there is absolutely no restriction on how long you can keep getting S, the start symbol, in the case of this grammar, you actually can generate an infinite set of sentences, right? So as you can see, a grammar is a finitary representation of an infinite set. A large part of computer science, mathematics, and logic really has to do with how to represent infinitary objects in a finite manner, and this is one such example. Yeah. So as I said, some of the warnings and cautions that you must keep in mind are that the set of non-terminals and the set of terminal symbols should be disjoint, and we have got the production set is really a binary relation from non-terminal symbols to strings of non-terminals and terminal symbols, right? So the replacement rule allows you to choose any non-terminal symbol and replace it by a string consisting of terminal and non-terminal symbols. Yeah, there is a star here which is to denote that you can replace that this set is really the set of all possible finite strings that can be generated from this set N union T. Okay, so I'll explain some of this. So in general, for any set A, A star is the set of all strings of finite length. In particular, the finite length could be a length of 0. Okay? So a 0 length string is really nothing. Okay? It's called the empty string, and we usually use the Greek letter epsilon to denote it. Yeah? A plus is the set of all non-empty strings generated from this, set of all non-empty strings of this. There is only one string of 0 length, that's the empty string. Okay, so it's the set of all non-empty strings, and A plus is equal to A star with epsilon removed from it, since there is only one 0 length string. Yeah, so the particular kind of grammar that we have been considering as an example is what is known as a context free grammar, right? So when the production rules are such that you are allowed to replace a single, the rules are such that on the left hand side of the arrow mark you have a single non-terminal symbol, and on the right hand side you have some string of terminals and non-terminals, right? That is called a context free grammar. It's called context free as opposed to, for example, a context sensitive grammar, right? A context sensitive grammar has production rules in which, given a certain string of terminals and non-terminal symbols, you are allowed to replace them by some other, you are allowed to replace the non-terminal symbol by some other string of non-terminals and terminals. Okay, the meaning of context free here is that these production rules, like it says, so let's take a context, let's take our example and obtain, so for example in this, let's take an arbitrary string in this example, and we have, so we are replacing this s, let's assume we are choosing this arbitrary string. So this s appears in a context, and the rest of this is the context. Okay, similarly this s here, for example, appears in this context. Okay, and we are saying, and we are calling this grammar context free because we are allowing these replacement of s by a string of non-terminals and terminals regardless of what context that s appears in. Okay, so this is the context in which this s appears, and we have a uniform rule. The production rule says that it's uniform in the sense that regardless of what context the non-terminal appears in, you are allowed to do a replacement. Okay, as opposed to what might be called context sensitive. In a context sensitive grammar, you could, for example, specify that a certain non-terminal can be replaced by a string only if it appears in a particular kind of context. Okay, in particular you might define that context to be an empty context. Okay, so in general a context sensitive grammar is really more general than a context free grammar. Okay, you might look upon every context free grammar production as specifying a context which consists of the empty string. Okay, anyway, we'll go into that a little later, but let's first worry about some simpler grammars also. Yeah, so if it follows these rules, then it's context free. Let's look at languages. The language generated by any grammar is the set of all possible sentences that may be generated from the start symbol. For example, if you take the start symbol located in some context and generate a string, that string may not be in the language at all, unless that context itself could have been generated from the start symbol, right. So this is what we would call a language, and in general we would call it a language on the set of terminal symbols, and a language on a set of terminal symbols is a possibly infinite set of strings from the terminal set. That is, we are saying that any subset of T star is a language. And for example, here are some trivial languages that you can define on any set T. You have the empty set of strings, which is the empty language. You have this language consisting of a single element, the empty string. Okay. You have T star itself is a language, and T plus itself is a language, and in between you have a whole lot of other languages. So you might regard this T plus and T star as one extreme, and these the empty language and the language containing the empty string as the other extreme, and you can have lots of subsets in between. Okay. So, and they are all languages. The problem is that when you have a programming language, you have an infinite set of possible programs, and the problem is of defining exactly what grammar can generate that language, right. So we will say that, so just as we have defined grammars, we will also define languages in a similar fashion. But first let us go into a particular into some particular kinds of grammars called regular grammars. Okay. So in a regular grammar, every production is of this form. Supposing you take a grammar in which every production is of this form, where this capital A denotes a non-terminal symbol, this capital B denotes a non-terminal symbol, and this small a denotes a terminal symbol. Okay. In fact, maybe I should have made it black, but anyway, right. So if every production is of this form, then we call this a right linear regular grammar. Okay. The first thing to realize is that a right linear regular grammar is also a context free grammar. There is really no difference. Okay. A context free grammar allows productions which are not, for example, a right linear regular grammar means that on the right hand side you should have just one non-terminal symbol and one terminal symbol appearing in this order. The terminal symbol is followed by the non-terminal symbol. In a context free grammar we do not have that restriction. For example, we had S goes to, so in a context free grammar, for example, if you take this, you take any of these rules, they are not at all regular. Okay, they are not right linear or regular. And of course you might also allow, you would also allow just a terminal to be generated, right. Right. So after all, you have to generate strings of the language from the terminal set. If you always had only always had non-terminal symbols appearing on the right hand side, then you will never be able to generate a full sentence of the language. So a right linear regular grammar is one all of whose productions are of this form. Similarly, you might define a left linear regular grammar as one in which all the productions are of this form. Yeah, and of course it has this terminal generation rule too. Yeah, so every production is either of this form or of this form. Then you would say it's a left linear regular grammar, right? So let me write that out for completion. Right. So such a grammar is called a left linear grammar. Yeah? And if you have done some hardware, if you have defined, if you have, for example, designed some hardware using finite state machines, it turns out that you can actually, all right linear grammars actually represent finite state machines. You know, machines machines without output. I'm talking of those kinds of machines, right? So in fact you can represent all, you can take the state transition diagram of the machine and refer to each state as a non-terminal symbol and refer to the input symbol, the input into that state, as a terminal symbol. So a finite state machine automatically defines a right linear grammar. Yeah. So most finite state machines have a start symbol. The start symbol is the start state, right? So what we are talking about is really quite a powerful language, and let's summarize what we have looked at. The general properties of grammars are that firstly, every regular grammar, whether right linear or left linear, every regular grammar is also context free. Every context free grammar is also context sensitive. In particular, all the productions of the context free grammar can be considered to be in the context of empty strings on both sides of the non-terminal symbol. So in general, we can look upon any string. For example, if you were to take a string like this, if you were to take one of these strings, I can think of any of these strings as, let's take the topmost string, right? I can take any of these strings as having a not symbol, then an empty string symbol, then an open bracket, then an empty string, and then an empty and then a and an empty string and a close bracket. Okay, so you can look upon every context free production as being padded, appearing in a context which contains the empty string, and the empty string implicitly appears everywhere between terminal symbols, between terminal and non-terminal symbols. Yeah. So it's for that reason that every context free grammar is also context sensitive. And what also is true is that every right linear regular grammar cannot, so our interest in grammars is ultimately in generating languages. So you take any language, supposing that language can be generated by a right linear grammar, then it is also possible to define a left linear grammar which will generate the same language. Similarly, if you were to take any language generated by a left linear grammar, left linear regular grammar, then the same language can also be generated by a right linear one. Yeah.
Can you please explain how context-free grammar is also context sensitive?
Sure. Okay. So what we have as a general kind of production, let me just rewrite that. So let's look at the set T star. Yeah. So the set T star for any set of terminal symbols, okay, is just the set of all strings obtained by this terminal symbol, okay, obtained from T. In particular, I can look upon T star as consisting of the empty string, okay, the set of all strings of length 1, which is the set T itself, the set of all strings of length 2, which is like T cross T, the set of all strings of length 3, and so on and so forth. Right? So T star is really the set which is obtained as a union of Cartesian products Tn, where n is greater than or equal to 0. Right? Now what I can do is I can define a binary operation called catenation. Okay. The effect of catenation is to take one string, is to take two strings and put them together. Okay. So for simplicity, let's assume that this set T consists of just two symbols. Okay. So let's just call those two symbols A and B. Right. So I can take a string in T star. Let's take a string in this set. So let's say A B A B B. Let me take another string. Let's say B A B. The operation of catenation, okay, which I'll denote by just a dot for the moment, is just to produce the string A B A B B B A B. Fine. So this is equal to just, so the operation of catenation just juxtaposes the two strings. It's a binary operation on strings. It just puts those two strings together and gives you a new string. So for example, this string is of length 5. So this belongs to the set T raised to 5. This string is of length 3. This belongs to the set T cube. And this string, it has a length 8 and it belongs to the set T raised to 8. And of course all these sets are subsets of T star. And so catenation is really an operation from T star cross T star to T star. Right? So it has a functionality which is to take two strings of finite length and juxtapose them. Yeah. So supposing you consider the empty string, okay, what happens when you take a string and juxtapose an empty string to it? You get back the same string. What happens if you take the empty string and to it you juxtapose some other string? You get back the other string. So the empty string satisfies these conditions, that for any string in T star, for any S belonging to T star, S concatenated with the empty string equals S, and the empty string concatenated with S also gives you S. So the empty string is very often, since catenation is just a juxtaposition operation, we just get rid of the dot symbol, okay, but you could have a dot in between, right? Now what you are saying, okay, so now one obvious property now is that this epsilon is in fact the identity element for catenation. It's like a 0 for addition, right? Secondly, catenation is associative in the sense that if I take 3 strings S, T and U and I catenate them, I can catenate them in any order. Okay. So the set T star under catenation and with the empty string is really a monoid, because this operation is associative. So catenation is associative, and it has an identity element. However, it is not commutative, so it's not an abelian monoid, it's just a monoid. Yeah. Now what do we mean by a context sensitiveness? So if you have a production, let's take a production, let's take a production of an arbitrary context sensitive grammar, okay. So let's keep this here so that we might in fact need it for some reason. So if you were to take a production of a context sensitive grammar, what it specifies is that I have a non-terminal symbol A, and if it appears in some context, okay, let's say, okay, then I can replace this non-terminal symbol by some other string. So which means that the context still is going to be preserved, okay, but this A is going to be replaced. So it's a conditional rewrite rule. I can replace A by let's say some B, C, and maybe some X, Y, Z, some X and Y padded with some, I don't know, some X and Y, okay. So what this production says is that I can replace A by the string X, B, C, Y only if on both sides of the A I have small a and small b appearing, otherwise I cannot do that, Okay. In that sense, this production is context sensitive. Okay. It says that if supposing there was some other symbols appearing somewhere on two sides, so there is a large in the generation process, there is some large string which is there is an arbitrary string, and it turns out that there are some other symbols which actually are around A. Let's say, yeah. Okay, supposing, so A here appears in a context which does not contain this, which does not contain small a and small b on either side. Okay, so then A appears in a context in which this rule cannot be applied. Okay, so a context specifies a certain minimal a minimal shell within which that thing should appear. In the case of a context free grammar, you are implicitly specifying that the context in which it should appear is epsilon on both sides. Okay, so any of these strings, okay, in this case, in the case of our context free grammar, in the case of our context free grammar, we are implicitly specifying that if S appears in an empty context, which means that you don't care what appears on either side of S, then I can replace S by A. Okay, so a context really specifies the smallest kernel that you are around that symbol which you should satisfy. And here it's the small, what we are saying is, regardless of what the string in the generation process is, if it is of the form A AB, okay, regardless of what else occurs in the string, if you can, this A is a candidate for replacing by this rule. Okay, context sensitive grammars are actually more general, I mean, in the sense that this padding of A and B is also perhaps not necessary. I mean, you might get rid of this A, small a and small b too. Okay, but let's not worry about it. The intuitive meaning of context sensitiveness is really that. What is, you are specifying some minimal padding around that non-terminal symbol which will enable a rule to be applied. And in the case of a context free grammar, the minimal padding is nothing. Okay, so all those rules can be thought of as rules in the context in which on both sides of the padding, the minimal padding that you require is the empty string, which means you don't really care what the rest of the string is in the generation process. Regardless of what the rest of the string is, you can apply that production. Yeah? Actually, it turns out that context sensitive grammars are what our programming languages all are. But there are practical reasons why we do not take their context sensitivity into account. It's much simpler to deal with the programming language as a context free grammar, as generated by a context free grammar, and deal with the context sensitive aspects later on in the process of compilation. Okay, a typical context sensitive feature, even in languages like Pascal, is that no variable can appear in a statement unless there is a declaration of that variable. Okay, only then. So if you had a context free if you have a context free grammar for Pascal, what it will do is it will fail to check on these context sensitive issues. Okay, so undeclared variables can appear in your program in your program if you just go by context freeness, but the practical reasons are that there are no efficient algorithms to recognize or parse context sensitive languages represented as context sensitive grammars. We have efficient algorithms to recognize and parse context free grammars. If you take context sensitive grammars, then you are not likely to get a linear algorithm ever. There are no linear algorithms available, linear time algorithms available for parsing context sensitive grammars. So what we do, what is usually done by many people is to, in specifying the language, is to specify it as a context free grammar, so that, and later as part of the semantics specify its context sensitive aspects. Many people in fact consider context sensitive to be synonymous with the semantics of the language, but that is not quite true. Yeah, right. So coming back to what we were saying, so every regular grammar is context free, every context free grammar is context sensitive, every language generated by a right linear regular grammar can also be generated by a left linear regular one, every language generated by a left linear one can also be generated by a right linear one. And we can in fact go, supposing you have a grammar which is regular but not necessarily right linear or left linear. What does that mean? It means that some of the rules might be right linear, some of the rules might be left linear. Such grammars can also be always converted into either purely right linear ones or purely left linear ones. Yeah. In fact, that conversion is what helps us to design machines for recognizing languages of these grammars. Yeah.
Can you give an example for that to convert it?
Well, it's not absolutely important now. It's really the subject of a theory of computation course. So we'll just, yeah. So when we are looking at languages, we would say that a language is regular if there exists a regular grammar which generates it. Similarly, a language is context free if there exists a context free grammar that generates it. And a language is context sensitive if there exists a context sensitive grammar that generates it. It is possible that for some language you have generated a context free grammar, it is context free but the language could still be regular. Yeah. So similarly, I mean, it's possible that you've written a context sensitive grammar for a language which actually could be context free, in the sense that if you work hard enough you might be able to come out with a grammar which is context free. Yeah. So let's just look at a few small examples of let's say regular languages. Yeah. So here is, take our Arabic numerals. Let's remember one thing. It's one thing to design a grammar and then ask what is the language generated by the grammar. Okay. Another thing is to take an existing language and try to define a grammar for it. And our numerals were known long before any grammar was used for them. Actually, a large number of our numerals actually comes from the notion of a grammar in natural language. And Sanskrit grammar, for example, was always a very neat, rigorous art form, if you like. So that's one of the reasons perhaps that we have such a neat we have evolved such neat notation for our numbers, right? So take the Arabic numerals. The terminal set is the set of all possible digits that you have. 0 I'm considering representation in decimal, so 0 to 9, and I require just one non-terminal symbol S, okay, and I have just these following productions. S goes on a S can be replaced by a digit followed by S again, or S can be replaced just by a digit. Okay, it's a very nice and simple grammar, right? So, and this is a right linear grammar, and the corresponding left linear grammar which is equivalent to it is this. If you were to take Roman numerals, firstly, it's not at all fully clear what the terminal set is, in the sense that the Romans never considered things beyond a few tens of thousands. The Romans had a pattern in the sense that a 5 every so they had 5, 10, 50, 100, 500, 1000. They had symbols for all of them, and assume that they had symbols also for 10,000, 50,000, 100,000, 500,000. So, but then you would require, if you continued that pattern, then you would require an infinite set of terminal symbols. Okay, supposing you did have that infinite set of terminal symbols, which means your condition for being a grammar already is violated, but supposing you could have an infinite set of terminal symbols, then the way the numerals are written is that they were very, very context sensitive. For example, an X cannot precede a C, for example, a X which is 10 cannot precede a V which is 5, or rather, I am sorry, an X cannot precede, let us say, D which is 500. Okay, so it's very context sensitive what can appear on the left of what and what can appear on the right of what. Okay, in that sense, the Roman numerals is not as simple as this. A regular language is implicitly a very simple object. It's easy to see what language it generates very often. It's easy to construct a grammar for it. Yeah. So that's, and also so what we would say is that these two grammars are really equivalent. So after all, remember that our ultimate aim is to represent languages somehow in a finitary fashion. So what should be the criterion for saying that two grammars are equivalent? They should have, well, let's say the same terminal set. They need not have the same non-terminal set. They need not have the same production set. But the language they generate should be the same. Right? So for the language that we have for the context-free language that we have previously given, here is an equivalent context-free grammar. Yeah. So for example, what I have done in this case is to just factor out the the open parenthesis and the S, and introduce a new non-terminal symbol called B, for which I have two rules. So I have gotten rid of the non-terminal symbols A and V, and C I gotten rid of because I directly wrote this, but I could have had C if I had wanted. Right? So shall we just quickly go through, shall we just quickly see that grammar? Here's the grammar. So here was the original grammar, and here is the equivalent grammar, in which what we have done is we have taken this, the fact that there is a common occurrence of a left parenthesis followed by S, we have factored that out into this. Okay? An equivalent way of writing this grammar is to use a new symbol S, let's say S arrow D, and let D produce this string. Yeah? The elimination of this C was just just to make the grammar smaller, to reduce the number of non-terminals. It is an important constraint. It's an important thing to reduce the number of non-terminals, because your parsing of the language really depends upon how many non-terminal symbols there are. Okay? So it's a good idea. So which means that for the same language you might have a variety of grammars. It's a matter of decision making to choose the right kind of grammar, the right correct kind of grammar which generates that language. And the criteria for choosing a grammar are that, firstly, that grammar should not be so complicated that it's impossible to parse the language. Preferably it should be a context-free grammar. Keep the number of non-terminals low. And another important constraint which we will not be able to appreciate now, which we will come to later, is that it should facilitate an easy explanation of the semantics of the language. In fact, the Arabic numerals are the left linear and the right linear ones, they have that difference. They are both equivalent in terms of actual generation, but the fact of the matter is that it's easier to specify a semantics for the left linear one rather than the right linear one. No, it's easier to specify a semantics for the right linear one rather than the left linear one. And certain parsing algorithms actually will choose the right linear over the left linear, because there is an inherent constraint in those parsing algorithms. Yeah, the inherent constraint has to do with recursive calls. Okay, so as you can see, the recursive calls in this case could lead to an infinite recursion, whereas in this case they would lead to a finite recursion based on a look ahead. Yeah, we'll look at that later. So that's basically all that we have time for today. Thank you.